we had finished yesterday's lecture by defining the commutator in a group. So G is a group, and A, B are elements of G, and the commutator is of A and B is this product. Okay. As I mentioned yesterday, there's another definition which I'll put under parentheses, in which you take A, B, A inverse, B inverse. This is the commutator you use when you do things from the left, whereas I do them from the right. Why is it called a commutator? Because we have seen that AB, it's immediate, it's BA multiplied by AB, by the commutator, because of course A cancel with the inverse and then B cancel with B inverse. So this means that two elements commute if and only if the commutator is one. So it measures whether two elements commute or not. And I have also noted or given an exercise, which is very easy. It was the inverse of a commutator. Well, it's the inverse of this object. And of course, we know that we have to take the inverses starting from the end, and the inverse of A inverse is an element itself. So this is BA. So inverting a commutator gets you the commutator in the other direction. And then for A, B, let's say subgroups of G, usually you do it with subgroups, but you could do it with subset as well. One defines the mutual commutator of this as the subgroup generated by all commutators A and B, where A is in A and B is in B. Okay, so okay, and that's there's a particular case when the two subgroups are the same and equals G, then this, which is that which is thus defined as the span of all commutators where A, B are in G, is also called G prime, or we'll have another symbol yet another symbol in a second, that is called the commutator subgroup, commutator of derived subgroup. Of G. And yes, I think I stated this yesterday too, to prove that if you take the symmetric group, its derived subgroup is a n for n greater or equal than 2, and then an prime equals an for n greater than or equal to 5. I mean, you'll find suggestions in the notes. Good. So this is what we were doing yesterday, and there is a part of group theory is called commutator calculus, which has to do with commutators. We'll have to do something like that for soluble groups, but we limit ourselves to very simple case. So we will show that commutators are sort of bilinear, that is sort of linear in the two components. So again, G a group. This time we take 3 elements. Okay, and we consider a commutator between A and the product BC. So it's nearly true. I mean, the formula I'm writing will only be valid when we get to the end. This equals AC times AB. So note that I've taken first the commutator with A and the second element here, and then the one with the first one. But this cannot be correct because this commutator ends with a C, because this is A inverse, BC inverse, and ABC. And so you put a C here, which means conjugate by okay, the usual symbol. This means conjugate by Y. Okay, let's prove this. And the proof goes like this. It's well, it's tricky, but elementary. So what's ABC? This is the inverse of A, then the inverse of BC, and then A, and then BC. So A inverse, B inverse, and I'll leave some room. No, sorry, of course, I was doing it wrong. This is the inverse of BC, so it's C inverse, and then I leave some room, then the B inverse, A, B, C, okay? So you see, this begins like A inverse, C inverse, so it's part of a commutator, and it becomes a full commutator if you insert AC, and there's a time-honored trick in algebra. You can add something, you can multiply, but then you have to multiply by the inverses, okay? So I inserted AC, but then I multiply with C inverse, A inverse, and so they cancel out. So look, this is just the commutator AC, okay? This thing here is just a commutator AB, okay? And then you see you are conjugating with C, this conjugate here. So we have proved the formula, okay? There is a similar formula which I won't prove. What happens if you do ABC, okay? And the trick to remember this is you always start with first element commutator with the last one, and then you take the other one, and then you fix. There's a conjugate somewhere. I mean, this thing starts with A, B inverse, blah, 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 and this is B inverse, A inverse. And this is not right because this starts with A inverse, so you conjugate with B, and that's it. This is a way of remembering. It's not a proof, of course, but the proof is absolutely similar to that. And there's a nice application to this because if you have A, B, so this is an exercise, but I'll work it out. It's exercise 3.1.8 part 2. If you have two subgroups of A, B, then A and B are contained in the normalizer in G of the subgroup generated by A and B. Okay, we could, it's a lemma though. Okay, how do you prove this? So the normalizer, which we have learned when speaking, for instance, talking about the Syloh's theorems, is the set of elements. Let's recall it here. The normalizer in G of H is the element of G for a subgroup G H of G, such that the conjugate, the usual conjugate we have here, of H equals H. Is the stabilizer of H in the action of G on its subgroups by conjugation, okay? And how do you prove this? You have to use one of these two. Well, let's prove, for instance, that, just a second, that let's prove that B is contained in normalizer. So you prove that B is contained here in the normalizer by using one of the two identities, and then you use the other one to prove that A is contained. And let me check whether, yes, so I have to use the first one, okay? Because if you take B, C in B, okay, then this equation here tells you that A, B to the C, note the C is in B, is equals, I take this to the other side, equals AC inverse times ABC. You see, A is in A. Oh yes, of course I take A in A. C is in B. A is in A, and this is in B, of course, because both B and C are in B. So all of this is an element of the span of AB. Okay, so since the span of AB, as we saw as you saw, is generated by these elements, as we saw in the previous slide, previous board, this shows that B is in the normalizer of AB. And you can prove that A is contained in normalizer by using the other, well, it's really symmetrical, but you can use the other identity. Okay, you take A and B. Well, of course, then the letters are a bit mixed up, but it's not terribly important. Good. Let's prove some properties about derived subgroups, the commutators and the like. Lemma So the first thing is the lemma is let GH be groups. Phi from G to H a morphism, a group morphism. And AB elements of G. Then the image under phi of a commutator AB is nothing else that the commutator between the images. Well, okay, I'll state and prove things one by one. And the reason is very simple, because when you apply a morphism to a commutator, the commutator is built up by products and inverses. And a morphism, by definition, preserves products, and then we proved already in the algebra courses that it preserves inverses. So you can really, this becomes simply the following, okay? Because it disperses products, so it's the product of the phi of the single elements and phi of phi, okay? I'm switching back and forth between the two pronunciations. Phi of A inverse is nothing than the inverse of phi A. And of course, this is exactly this commutator. So commutators preserve their form under morphism. The second thing tells you that G prime, so remember this can be also written like this, and it is the span of all commutators, is a fully invariant subgroup of G, meaning that if phi is an endomorphism of G, meaning just a morphism from G to G, then phi of G prime is equals phi of G prime, sorry, phi of G prime, and it's contained in G prime, okay, for all endomorphisms. Note, since it's fully invariant, that is, sent to itself, into itself, by any endomorphism, is also characteristic. Since the automorphisms are a subgroup of the semigroup of endomorphisms, it follows that G prime is also characteristic. But there is an exercise that I will state in a second, that you see the center is characteristic, the center of a group is characteristic in the group, but the center is not necessarily fully invariant. I'll state the exercise in a second. So the center is weaker from this point of view with respect to the derived subgroup. There is a reason for that, but a deeper reason. Why is this so? Well, the proof is really the proof we had already seen, because since the image of a commutator under phi is a commutator, this is really yes. This is what this is phi of the group generated by this AB. Okay, and the group phi of a group generated by certain things is nothing else than the group generated by the images. This is something when we should have seen in Teoria dei Gruppi, and this is and this of course is nothing else by the previous step, that the subgroup generated by the commutators between images, this phi of G prime, the derived subgroup of the image of G under phi, and this is generated by certain commutators, so it's certainly a subgroup of G prime, okay? Because all of these, of course, are in G prime. They may, I mean, this might be smaller. For instance, if phi is the endomorphism that sends everything to 1, this is 1. but since it's generated by commutators, and this is by some commutators, and this is generated by commutators, it has to be contained. So before okay, yeah, the exercise, I'll try and remember. Point 3 is might look like a very small thing, but it's quite useful. And it says that if K is a subgroup of G, then the following are equivalent. The first thing is something well known, that K is a normal subgroup of G. And the second one is that the commutator between K and G is contained in K. This is extremely simple, as we will see in a second, but it's important. It's so much important that, for instance, I'm a group theorist by trade, and I tend to think of normality of a subgroup in these terms, as two, not as one, okay, which is defined by conjugates and so on. And the proof of this is very simple, and is based on the fact that I think we noted already yesterday, that if you take A and multiply it by AB, what do you get? You get A times the commutator. These two cancel out, of course, and what you get A conjugate through B, okay? So there is this simple relation. So if A is in K and B is in G, okay? So let's say we get that. So for all A in K and B in G, to say that A to the B is in K, which means K is normal in G, okay? Since A is in K, is equivalent to say that the commutator is in K, okay? Because, I mean, you have an element of K multiplied by this equals this. So if this is in K, this is the product of two elements of K, so this is in K. Conversely, if this is in K, then AB, as you see, is nothing else but A inverse and the conjugate. So again, if this is in K and this is in K, then this is in K. So since A is in K, this is in K, if and only if this is in K. And this proves the fact, because this means that it's normal. And if I quantify for all A in K and B in G, this means that the commutator between K and G is contained in K, okay? So we will be exploiting this in a second. So normality of a subgroup can also be stated in terms of the commutator between K and G, okay? So the subgroup generated by all commutators where the first component is in K and the second component is in G, okay? Good. And we'll, yes, here's the exercise. Show that the center of G, well, G, of course, is a group. If I don't say anything, G will be a group, which is, as you remember, the set of Z in G, such that ZG equals GZ for all. G in G is a kernel of a certain, of the morpheme iota that we considered a couple of lectures ago, is a characteristic in G. So it means it's sent to itself by all automorphisms, but in general, not fully invariant. So what are we saying? Remember of this omega subgroup things we discussed. Characteristic means omega subgroup when omega are the automorphism group. So the center is sent to itself by all automorphisms, but there will be at least an example where there is an endomorphism, which of course won't be an automorphism, that does not send the center to itself. Hint, for instance, I think the simplest example is S3 times C2. There is the symmetric group on 3 elements, direct product with cyclic group of order 2. I leave to you the details. Okay, so you see that the center is somewhat weaker than the derived subgroup from the point of view of these properties. Okay, now let's see a very important property of the derived subgroup, which can be stated informally, well, not absolutely formally, to say to the effect that G prime is the smallest normal subgroup of G, such that the quotient is abelian. So let's state it like this. Let G be a group and H be a subgroup of G. Then the following are equivalent. Without the then. The following are equivalent. So one says that H is normal in G, and the quotient, once you know that it's normal, you can consider the quotient is abelian. Okay, and the second one is simply that G prime is contained in H. And so you see, once we prove this, it will follow, say, corollary. You see that a normal subgroup is part of this as abelian factor group if and only if G prime is contained in H. Of course, G prime is contained in G prime, so we will have in particular that G prime, G over G prime is abelian. So G prime is the smallest normal subgroup of G, H of G, such that G over H is abelian. Okay, this should be clear because G prime is contained in every subgroup, normal subgroup of this form. Let's see how to prove this. So, well, the corollary is somewhat immediate. So let's see the proof of the proposition of, I said D. Assume 1, okay? So we prove that 1 implies 2. Okay, so we know that H is normal. We know that the quotient is abelian. What does it mean? Well, the quotient, of course, as usual, is formed by the cosets. Left or right is the same, and take the left cosets. So since the quotient is abelian, this means that for all A, B, and G, we have that the commutator AH, BH is equal to H. It's trivial. This is the identity of the quotient group, okay? H equals 1H, if you wish, is a coset, of course. But this commutator, well, if you want, is a particular case of the lemma we had, because we are considering, say, the morphism. Okay, so this is a particular case of something we were seeing earlier, because if you consider the standard morphism from G to G over H, we send X to a coset. This is nothing else but that phi A, phi B, okay? So equals phi A, B, okay? This is a particular case of something we saw earlier. So this is ABH, because it's the image under this phi of the commutator. So we have that this equals this for all A and B in G. But of course, this means that what does it mean for all these cosets to equal H? This means exactly that for all A, B in G, A, B are in H, okay? Because you remember that there's a standard fact that a coset equals H if and only if G is in H, okay? The standard fact about equivalence relation. So we have seen that assuming 1, for all A and B in G, the commutator is in H. Now G prime is generated by AB, by this commutator. And of course, the subgroup generated by certain elements has the property that if there is, it's the smallest subgroup containing all these generators. Since all these elements are in H, this then is contained in H, okay? Because H is a subgroup containing all commutators, and G prime is the smallest, by definition of the generated subgroup, the smallest subgroup containing all commutators. So what have we seen? We've seen that if a subgroup is normal and the quotient is abelian, then it contains G prime. And now let's see the other direction. Assume 2. Okay, so we have to prove two things: that H is normal and that its quotient is abelian. How do we prove that H is normal? Well, we use this property. So assume 2, that is, G prime is contained in H. How do you prove that H is normal? Well, you consider the subgroup generated by these commutators. And according to the lemma I proved earlier, we have to prove that this is contained in H. But this, of course, is generated by certain commutators. And so this is definitely a subgroup of G, okay? Because this is generated by commutators of an element of H and an element in G. And so, as a particular case, is the commutator is generated by, this is generated by all commutators. But this is G prime, of course, so it's just a different way of seeing, of writing it. And by assumption, this is contained in H. So this is contained in this. As we saw, you'll have to get used to this, but this means exactly that H is normal in G, okay? So we have just used this property that to say that the subgroup is normal in G is enough to, well, is equivalent to showing that the commutator between H and G is contained in H. And now we have to prove the other thing, that is that G over H is abelian, but this is not complicated because if, well, let's say for all, A, B in G, we compute, we have a quotient group, okay, because we compute this in the quotient group because now we know that H is normal, and this is equals A, B, H, but this is something in G prime, and by assumption G prime is contained in H. So what's this class? Well, this element is in G prime, which is contained in H. So by the standard fact that I recall, this is just H, the identity of G. So we have proved that for all A and B in G, this commutator is trivial, okay? Because this is the identity in G over H, trivial in G over H, which means that that G over H is abelian. So G prime has this important property. It's the smallest normal subgroup with abelian quotient group. Good. And with these premises, we are ready to talk about soluble groups. I probably already used this title. And soluble is the British way of referring to these groups. In America, they tend to call them solvable. Okay, so it's the same thing. It's just different. Okay, different ways of referring to them. Okay, so first of all, given a group G, any group is not necessarily finite, we can consider its derived sequence. Note the choice of word, the sequence. What's this? Well, we start with, oh, there's a mistake in the notes. We start with G to the naught. The first term is G. So G to the naught among parentheses. Then G to 1, between parentheses, is nothing else but G prime, okay? The derived subgroup. What's the next? G2 is the derived subgroup of G1, which was D prime. And in general, Gi plus 1 will be the derived subgroup of Gi. So we start with a group and keep taking the derived subgroups, okay? I take the derived subgroup, so I take the derived subgroup of the derived subgroups. This, you can write this and you'll find this sometimes written G double prime, because after all, G1 is just G prime, so this double prime, and so on. But of course, when you have several terms, it makes no sense writing at 1000 primes. I mean, you write G to 1000. So note that in general, in a group, this sequence can be rather trivial. For instance, the previous exercise shows that if n is greater than or equal to 5, we have I left you as an exercise to prove that an prime is an. And so what happens if you take this series? This is the alternating group. If you take this sequence, sorry, not the series, in the alternating group, well, simply that all terms will be the same, because you keep taking the derived subgroup of an, but it is always an. So in this case, we have ani equals an for all I. Okay, because you take the first derived subgroup and you stay there, and so on. So it's not necessarily a series, because for a series, except the fact that I'm numbering from the top instead of numbering from the bottom, you need this sequence to get to 1, a sequence to go from G to 1. And so here's the definition. A group G is said to be soluble or solvable, sorry, if the derived sequence is a series. So what it means to be a series, that it starts from G, and this is okay, because you start with G, and it ends with 1. That is, there is n such that G to the n is equal to 1. I'll sometimes write 1, simply 1 for the trivial subgroup, but here I'm being proper, and I've written it with the braces, okay? It starts from G naught, which is G, but I mean, if it ends with 1, then it's soluble. Note that this definition applies even to infinite groups. What's important is that this series terminates in a finite number of steps, okay? Because there has to be an n such that this happens. For instance, you can example, this is a bit trivial, well, a couple of examples. You have then S3, if you take S3, the derived subgroup is A3, and then if you take A3 prime, this is a cyclic, or this is abelian, so this is 1, so it's soluble, okay? S3 is soluble. I leave this as an exercise. And then if you take S4, the derived subgroup is A4. If you take A4 prime, okay, you can see that this is a subgroup V of order 4. And we know that from theoretic grouping that a subgroup of order P squared, when P is a prime, is abelian, so V prime equal 1. So soluble, S4 is soluble. But of course, starting with S5 is not soluble, because, well, we'll come to that in a second. And by the way, you should know part of this, because the term soluble or solvable comes from the fact that say, a polynomial equation is soluble or solvable by radicals. There is a formula, like the formula for for equations of the second degree, if and only if the Galois group is soluble, okay? And the term soluble or solvable comes from that, because an equation is solvable by radicals if and only if the group is solvable, okay? Soluble or solvable. But so you should have seen part of this already in the Galois theory, which you have well taken. Okay, and now let's state a proposition that gives three equivalent conditions for a group to be soluble. These are very useful in proofs because we'll give some proofs about properties of how the properties of soluble groups under subgroups, quotient groups, and the like. There is a recurring argument in group theory when you define a sensible class of groups, and soluble groups are definitely sensible as they are. It's a good idea to consider them because they are connected so much with the properties of algebraic equations. So once you have a sensible class of groups, you want to know whether, for instance, a subgroup of a group with the property also has the property, or a quotient group has the property, or something like that. And we'll tackle these facts for soluble groups in a second. But first, we give two equivalent conditions. This is a typical, of course, of the mathematics you've seen in the past years. Sometimes the definition is not enough, and equivalent conditions are useful in particular cases. Since this is important, let's devote the next page to the statement. So proposition. Let G be a group. Again, I'm not assuming this is finite. The following are equivalent. So the first one is that G is soluble. Okay, so this means yeah, that is, there is n such that the n term of the derived series is 1. I've just written 1, omitting the braces, but it's the same thing. Then the next thing says there is a normal series so a normal series means an omega series for omega, the inner automorphism, which means all subgroups are normal in G. So G equal G naught containing G1 and so on. Well, actually properly, because a series has to be proper, so that Gn is equal 1. Okay, it's not just that, with all quotients abelian. So normal series means that that Gi is normal in G for all I. Okay, so all these terms are normal. The third is there is a series, just a series with the same property. But recall that a series, I'll recall this in a second, okay? When you have a series like this, you imply that each Gi plus 1 is normally in the previous one, okay? Well, I'm going from the top to the bottom, from the whole group to the trivial subgroup. So the higher index here denotes a subgroup that is smaller than this with a lower index. Okay, G naught contains G1, G1 contains G2, and so on. So we adjust that this is normal in this, but of course this is perfect enough to say that the quotients are abelian. Because I mean, to consider this quotient, I just need Gi plus 1 normal in Gi, whereas here Gi plus 1 will be normal in the whole of G, but this is overkill. So essentially, two of the steps are in the proof. I mean, how do you prove that these are equivalent? I'll prove that 1 implies 2 implies 3, and these are rather trivial, and then the 3 implies 1, but this is not difficult either. So you see, if G is soluble, then, so this is 1 implies 2. Then the GI, if you take GI to be G to the I, is a series as in 2. But this requires an explanation. So I'm saying, so 1, I'm assuming 1. So G is soluble, which means that there is a term of the derived sequence we get to 1. So the derived sequence is really a series, ends in 1. And I'm saying that if you consider a series where GI is the ith term of the derived series, then this is okay. Well, so the idea is the following. Let's prove that this is a normal series, really. So we have to prove that all these are normal in G. Yes, and this is important, yes. And the reason why they are normal is the following, that yes, I think, yes, I mentioned that before. And remember that, let's use a neutral letter. Let H be a group. We have proved that its derived subgroup is fully invariant in H, and in particular is characteristic. Okay? And the reason is that if you take any automorphism, the image of a commutator is a commutator. Okay, so if you apply an automorphism to this, to a commutator, you get a commutator. So you stay inside here. Okay, we proved even more that it's fully invariant. That is invariant under endomorphism, but in particular is invariant under automorphism. So you see, I have to prove, as I said, that these terms of the derived series are normal in G. Well, we know, we have proved earlier, we know that G1 is normal in G. This is G prime. Okay, we proved that it's the smallest normal subgroup with abelian quotient. Okay, now assume to have proved by induction, that GI is normal in G. And then you consider GI plus 1, which is the derived subgroup of GI. And then by this fact that I proved earlier, this is characteristic in GI. And now there is an important point. Recall that I gave a simple example in which a subgroup which is normal in a normal subgroup need not be normal in the big group. But characteristic in normal is normal, okay? So this is a characteristic subgroup of a normal subgroup, and this implies that GI plus 1 is normal in G. Well, I'll write the usual symbol. Because characteristic in a normal subgroups imply normal in the whole subgroup, okay? This is important. It's not enough to say normal here. You need characteristic plus normal to get normal, okay? So normality is not transitive, a transitive relation usually. But if you put characteristic first, then you get this. Okay, so what we have proved, that I want to prove that there is a normal series with abelian quotients. We have proved that the terms of the derived series are indeed normal in G, okay? And to show that they are abelian, well, this is obvious. And then GI over GI plus 1 is nothing else but, in this case, GI over GI plus 1. And this, recall, is just the derived subgroup of the previous one. And we have proved that a group over its derived subgroup is abelian. Okay, this is the smallest normal subgroup of this one, this is GI, which is certainly the quotient is abelian. Okay, so there we are. Okay, so we have proved that 1 implies 2. So if G is soluble, there is a normal series. This series is nothing else that derives. We'll say there can be many series like this, but one of these is the derived series. And then, of course, the normal series is nothing else but a series in which, moreover, the subgroups are not just, the terms are not just normal one in the other, but are normal in the whole of G. So clearly 2 implies 3, because a series like, a normal series like this, you forget that it's normal, you get a series like this, okay? You have the, say, GI plus 1 is even normal in G, so of course it's normal in the next. So 2 implies 3 is obvious. Clear, because a normal series is a series plus something else. Okay, so if you forget that it's normal, you get a series and you're all right. Good, but now we have to prove that 3 implies 1. So if there is a series, so I just assuming that 1 is normal in the next with quotient, abelian quotients, then I have to prove that G is soluble, that there is an n such that the nth term of the derived series is 1. Okay, so how do you prove this? Okay, so suppose 3 implies 1. Suppose that that you have a series G naught. You want no, sorry, the indices are, these are indices, not Gm equals 1 with abelian quotients. So a series in any case means 1 normal in the next. Okay, so let's start from the beginning then. We have that G1, since this is a series, by definition, its terms is normal in the next. So G1 is normal in G naught. And by this condition, G naught over G1 is abelian. But what we have proved, if you have a normal subgroup with abelian quotient, this happens if and only if G prime is contained in G1, okay? This is the sort of universal property of the derived subgroup. Is the smallest normal subgroup with abelian quotient, okay? And remember that G prime can also be denoted by G1 on top, okay? And now you see where I'm going. Proceeding by induction, assume Gi, that's the ith term of the derived series, is contained in Gi. This is the ith term of this series with abelian quotients, okay? So since by assumption Gi over Gi plus 1 is abelian, since Gi plus 1 is normal in Gi, okay, by definition of a series, and the quotient is abelian, actually, let's delete the since. The fact that Gi plus 1 is normal in Gi and the quotient is abelian, I forgot to mention this, is equivalent to what? Is equivalent to saying that Gi prime is contained in Gi plus 1, okay? That's again the same property I'm saying here. Every time you have a group normal in another with abelian quotient, it means the derived subgroup of the big one, G naught, which is nothing else than G prime. G naught is G, okay? Every time you have this, means the derived subgroup is contained here. So you have this group normally in this with abelian quotient. It means that the derived subgroup of the top group is contained in this normal subgroup. But GI, by an induction hypothesis, contains G to the I, okay? Okay, so GI contains this, so the derived subgroup behaves in the same way. And this is nothing else, let's put parentheses here, by definition, that GI plus 1. The terms of the derived sequence are defined exactly like this. So G1 is the derived subgroup. And then once you have defined G to the I, GI plus 1 is just the derived subgroup of it. And you see what we have proved here. We have proved that this is contained in GI plus 1. So we assume by induction hypothesis that the GI is contained in GI, well, of course, upper, lower, and you obtain the next. And so once we have this, what we obtain, well, let's finish here because we have some room. And what we obtained is that G to the M is contained in Gm, but this is 1. So we obtain that G to the N is 1. And this means that the group is soluble, because soluble means that there is a term of the derived series that gets to 1, okay? And right, so we have proved the equivalence of these three conditions, and we'll see them in action in a second. But first, yes. But first, we'll give another proposition with this, which is rather simple. Okay, let G be a finite group. The time is finite, okay? Note the finiteness. Then the following are equivalent. One, that G is soluble. And since the group is finite, we can speak of composition series. So remember, this is a series which cannot be refined further, whose factors are of prime order. And 3, the factors of any composition series are of prime order. I'm not saying that they are of the same prime order. They can have different orders, but they have to be of prime order. And this is useful also to review things we have just proved. 2 implies is equivalent to 3 because we have proved that 2 composition series may be different, but the factors are the same up to a permutation. So if there is a composition series whose factors are of prime order, if you take any composition series, it will have the same orders of factors, except they may be permuted. Think of the cyclic group of order 6. You can have 2, 3, or 3, 2. Okay, so 2 is equivalent to 3, and of course, let's say that 2 implies 1 is part of a theorem because part of the previous proposition, because if you have a composition series whose factors are of prime order, this means that the factors are abelian, and this is let's get back, and this is exactly this condition here, a series with abelian factors. Okay, so let's consider here 2 implies 1 because groups of order, because the factors of the composition series are abelian. A group of prime order, actually cyclic, okay? A group of prime order is cyclic. So this implies soluble, and 1 implies 2. Well, this is clear because you see, okay, so if G is soluble, let's back here. If G is soluble, then there will be a series, well, for instance, the derived series, which has all abelian quotients, okay? This is just a series. What's a composition series? Well, you start from any series and you start refining it. There is, if it's possible, you insert other terms between two consecutive terms of the series. Since these quotients are abelian, the intermediate steps will also be abelian. Let's write this well. 1 implies 2. So G is soluble. So by the previous proposition, okay, there is a series. Let's go to the next page. G naught equals G, G1. Well, I'm writing this, but actually, since it's a series, it has to be proper inclusion. G2 and so on. Gm equals 1 with the all quotients abelian. I mean, a series of all subgroups are normal in the previous one. But then refine this. This is a finite group. So you can start inserting more normal subgroups between two terms, and you will get, you have to finish sooner or later because it's finite. So there are only finite many subgroups you can insert. Refine this series to a composition series. So to a series that cannot be refined further. So this means that between GI and GI plus 1, I have inserted other terms. So, so suppose I have here an H and a K, okay? Right. And this cannot be refined further. But then H is a subgroup of GI, okay? And which contains GI plus 1. So H over GI plus 1 by the third isomorphism theorem is a subgroup of GI over GI plus 1. Okay? This is abelian, so this is abelian as well. A subgroup of an abelian group, of course, is abelian. So this is abelian. And then again, we use the third isomorphism theorem because this tells you that the quotient H over K, I have refined this, and so this K is normal in H. Let's put it here. This is isomorphic to H over GI plus 1 over the K over GI plus 1. Note that K also contains GI plus 1. Okay, so the part of the third isomorphism theorem tells you that here you can simplify the GI plus 1. And so this is isomorphic to a quotient of an abelian group. Okay, so abelian. So this is abelian as a subgroup of an abelian group. This one. And this is abelian as the quotient, as a quotient group of an abelian group. This one, okay? So we have used the simple fact that a quotient and a subgroup that's a quotient of an abelian group are abelian. I mean, this is quite immediate, okay? And with an entirely similar proof, which I leave as sort of an exercise, we can prove the following, that again, I have a finite group which ensures that you can refine a series to a composition series. You can refine an omega series to an omega composition series. Then the following are equivalent. G is soluble. 2, there is a principal series whose factors are elementary abelian, and 3, the factors of any composition series. No, sorry, principal. Are elementary abelian. So let's recall the terms. If you have a series, you can refer to called a composition series. So just series means every term normal in the next. A principal series is a normal series, okay? Okay, so it's a normal series. So every subgroup normal in the top group, in G in this case. And we have seen that the factor, if you have a finite group, the factors of a principal series are either elementary abelian or the product of isomorphic non-abelian simple groups. But again, since G is soluble, you have a series with abelian quotients, so you refine this to a principal series, and you obtain, say, a characteristically simple group, which is abelian, and we have proved that we have given a separate proof that this is elementary abelian. Okay, this shouldn't be difficult. Please try and fill up the details if there are problems. Just mention this to me. Okay. So this has to do, okay, reason in a principal series, the quotients of a finite group are either elementary abelian or say S1, okay, let's write direct product of several copies where S is a non-abelian simple group. But soluble means that there is a normal series with abelian quotients. If you refine them, the quotients exactly with the same argument for we used in the previous proof are abelian. And so once you get to the principal factor, to the factor of a principal series, they are abelian. So they cannot definitely be of the second form. They have to be of the first form, elementary abelian. Okay? Good. And with this in place, we can now give an important theorem. The really important one is the last one, because it's let's give a spoiler. Consider, for instance, the property of the abelian. If you have, we have just used two properties of abelianness. If you have an abelian group, every subgroup is abelian. If you have an abelian group, every quotient group is abelian. But you cannot put together two abelian groups and get an abelian group. For instance, S3 has an abelian subgroup, which is A3, and the quotient S3 over A3 as order 2, so is abelian. But of course, A3 is not abelian. So you cannot put together two abelian group and get an abelian, hope to get an abelian group. Whereas for solubility, it works. And this is important in the theory of equations. Let's prove this. Let's state this and then prove this. Let G be a group. Okay. First, if G is soluble and H is a subgroup of G, then H is soluble as well. So far, so good. I mean, a subgroup of a soluble group is soluble. We'll prove this, by the way. But it's not a strange thing. I mean, we are used to such properties. If G is soluble, well, okay, this is supposed to be soluble, but and N is a normal subgroup, then the quotient is also soluble. Okay? 3, which is really something, a way of reformulating 2, if G is soluble and phi from G to K, where K is another group, okay, K another group. I've added that K is another group. If phi to K is a morphism, then phi of K is soluble. The image is soluble. This will be immediate from the first isomorphism theorem. No, this is not phi of K. There is a mistake in the notes that I'll try and fix. It's phi of G. And this, of course, will be trivial because phi of G by the first isomorphism theorem is isomorphic to G over the kernel. And so it will follow from 2. But here is the important fact. If N is a normal subgroup of G, and both N and G over N are soluble, then G is soluble. Sometimes this is stated by saying that G is, the soluble by soluble means soluble, which means okay, means something like this. You have G, you have N, you have 1. So the quotient is G over N. If this is soluble and this quotient is soluble, then the whole group is soluble. This is not true, for instance, for abelian groups. Exercise show that 4 does not hold for abelianness. Okay, it's not true that if N and G over N are abelian, that G is abelian. Okay, and actually solubility is in a, well, okay, no, it's the best you can do if you start with abelianness. Okay, so let's prove these properties, and we are free to use any of the 3 equivalent conditions. Okay, and we'll find that some of them are more useful than others. Okay, so first one, if G is soluble, then a subgroup is soluble. And for this, we can use we can really use the definition. So suppose G is soluble, and we use the definition, which means that so G over N equals 1 for some N. These are the terms of the derived series, okay? And okay, but it's rather easy to see that if H is contained in G, I'll start with the first term, then H prime is contained in G prime. Perhaps we already used this, simply because this is generated by all commutators of element of H. But the elements of H are elements of G, so of course this is contained here. And this implies that Hi is contained in Gi for all I. Because you go on and get this. And so in particular, this implies that H to the N is 1. So H is soluble. So I've used just the definition, okay? Nothing else. The definition of a soluble group. Simply because the terms of the derived sequence, yes, of a subgroup are contained in the corresponding terms of the whole of G. Because, I mean, commutators of elements in H are particular instances of commutators of elements in G. 2, so 2 means if G is soluble and N is normal, then the quotient is soluble. Just to see, we'll use just to give an example of a different approach. So we have N normal in G, and we'll use the second equivalent condition for a soluble group, I mean, that we have proved in the previous proposition. So, and suppose that G0, G1, G2, and so on, Gm equals 1 is a normal series. with abelian quotients. I could also use the definition of solubility to prove this, but I mean, let's go this way. Then consider the following subgroups. Consider the following subgroups: G naught, okay, containing G1n, containing G2n, until Gm is 1, so this is n, okay? And of course, both the Gi are normal in G and n is normal in G, so these are all subgroups, and these are obviously normal subgroups. Okay, because they are the product of two normal subgroups. This is obviously normal. Note that this need not be distinct, but I mean, if some of them, for instance, if this is equal to this, we'll simply erase one of them, because in a series, we assume that the terms are distinct. But, and I claim that the quotient of two terms is abelian. I claim Gi n over Gi plus 1 n is abelian for all n, for all I, okay? And this is just a matter of using the second isomorphism theorem. So recall, this is a normal series with abelian quotient. So you know that the quotient of Gi over Gi plus 1 is abelian. And okay. And so I take this quotient. And the trick is the following: to insert Gi plus 1, which you can do because Gi plus 1 is containing Gi by assumption. This is a series. So Gi plus 1, so Gi plus 1 is nothing else but Gi. I mean, simply multiply by something that is in Gi anyway. But why this is okay? Because now we can assume, apply the second isomorphism theorem. We tell you that in this situation, this is isomorphic to Gi over Gi plus 1. So essentially, it tells you can erase these two terms, but not quite, because there's a trace left, and this is the intersection of this, okay? But note that this is, yeah, we are also using the third isomorphism theorem. So we know that Gi plus 1 is containing Gi, but of course, Gi plus 1 is also containing Gi intersect Gi plus 1, and because Gi plus 1 is containing Gi, and Gi plus 1 is obviously containing Gi plus 1n, okay, because this is a product of the two. So this was the second isomorphism theorem, but you can use the third, and this will tell you, it's the same thing we have used a second ago, that this is isomorphic to this big quotient. Okay, and so this is abelian, because this is abelian by assumption. Okay, and so this is a quotient of an abelian group. This is abelian as a quotient of an abelian group. Okay, and we are nearly there, because we have proved what? We have proved that that this is a, well, not a series, because you have to, it doesn't end in one, but we'll fix this in a second, that there might be repetitions, but in a way the quotients are all abelian. And then you have all these subgroups will contain n, because of course I have multiplied this by n. And so from this, okay, I'll copy and paste this, because it's, so you can see what's going on. Add to library, and then, because I have, okay, next, and then let me copy from the library. I think it's in pictures. It should be the last one. Yes. Okay, fine. There we are. You have this. And then again, the third isomorphism theorem tells you that, okay, so this is G, okay, that all these subgroups contain N, so this corresponds to subgroups of G over N. Until you get to N over N, which is, say, one, which is the trivial subgroup of G over N. And the point is that, again, by the third isomorphism theorem, if you consider the quotient of one of these over the next one, okay, again, you can simplify N, and this is isomorphic to GIN over GI plus 1N, and we have just put that this is abelian. Okay, so what we have here, if you delete possible repetitions, so deleting repetitions, because for a series, as I said, we insist on all terms being different, we obtain a normal series with abelian quotients for G over N. Okay, so here we have used property 2 of the previous proposition. The proof is really direct. We are only using third isomorphism theorem. This is third, and the second isomorphism theorem, which are really part of the grammar, basic grammar of group theory. Okay, so where we are, this is the proof of 2. Okay, now proof of 3, as I said, is rather easy because it tells you that you have a soluble group and the morphism, then the image of is soluble. Of course, you cannot say anything about K. For instance, the morphism could send all of G to the identity, and then of course you have no control on K. But to prove 3, you simply know that if you have phi, okay, from this, you simply know that this time we have the good old first isomorphism theorem, the isomorphism G over the kernel of phi, and by 2, this is soluble. And of course, isomorphism preserves solubility. This is rather immediate. Welcome. Good. And now we get to 4, which will conclude the lecture. This is the important point, so let's rewrite it here. So N is normal in G, N and G over N soluble implies G soluble. As I said, something that is not true for abelian groups is not true for nilpotent groups either. As I probably mentioned 2 years ago when I last gave this course, I also spoke about nilpotent subgroups. So these are not necessary for the course, so I left this as a seminar. And anyway, the same example of abelian groups shows that nilpotent subgroups don't satisfy this property. So let's see why this is valid for soluble groups. And this is critical. Here it's critical that we can invoke property 3, which means that to prove that a group is soluble is enough to find a series with abelian quotient, just a series, okay? Not a normal series or anything else. So let's see what this means. N is soluble. So there is a series which I'll start from 1. After all, it is not important if I start from one verse of the other. let me think of the letter I'm going to use. I'm going to use X. So this is X naught, say. Then X1 until X H, okay, which is N, a series in N, okay, where with Xi normal in Xi plus 1. I have started numbering from the smaller one, so this time is the lower index that is normal in higher index, but I mean, it's obvious if you look at this, and the quotient Xi plus 1 over Xi is a billion. Okay, so N is soluble, and so this means there is a series like this, just a series, okay? All terms are normal in the next. Why is this important? Because, for instance, if I insist, if I'm talking about a normal series, well, I can have subgroups that are normal in N, but then I cannot get a normal series of G, because I mean, subgroups that are normal in N, remember, normality is non-transitive. So if these normal subgroups are normal in N, they need not be normal in G, okay? Normality is not transitive. Whereas if I just insist on each of them being normal in the next, there is no problem. Okay, so N is soluble, that's dealt with. G over N is soluble. So this means that there is a similar series, okay? And we'll write it. There is a similar series, why not? Okay, more about this in a second. Y1 and so on until Yk, which is G over N, okay? Why not? What is why not? Why not is nothing else than the trivial subgroup of G over N. And we saw that this is just a subgroup the subset consisted of N being the identity of G over N, okay? And so this is G over N. But third isomorphism theorem, what are the subgroups of G over N? Subgroups of G over N, okay, so sorry, with yi normal in yi plus 1 for every I, okay? What are the subgroups of G over N? The third isomorphism theorem tells you that yi is nothing else but zi over N, okay? For remember, this is normal in G over N for some zi. I'll start writing this, which is a subgroup of G, okay, containing N. Okay, so what are the subgroups of G over N? Are of the form a subgroup of G containing N over N. But this yi is normal in G over N, and this means that zi is normal in G. Okay, it's so subgroups of G over N correspond to subgroups of G containing N. Normal subgroups of G over N correspond to normal subgroups of G containing N. Okay, so we have this thing. We start with this, and then we have Z1 over N, okay, until ZK over N, which is just G over N. Okay, because I mean, here I had the yi, but each yi is nothing else but this. And remember, this series of yi, not only this holds, but the quotient are abelian. Okay, G over N soluble means that you have such a series with the quotient abelian. So let's write not only this is normal in this, but each of these quotient is abelian. For all I, I'm not writing down the quantifiers. Okay, so we have that yi plus 1 over yi is abelian. That is, let's see, yi is of this form, so this is zi plus 1 over N over a big one, so we know which comes first. Zi, this is abelian. But the usual third isomorphism theorem tells you that this is isomorphic to Zi plus 1 over Zi. So look what we've done. We start from 1, and which is y naught, containing y1, and so on until we get to n, okay? Not that z naught is equal to n, okay? Because this is n over n. And then we go on, because the fact that zi over n is contained in zi plus 1 means that this is contained in z1, and so on until zk, which is g, okay? Zk equals g. And so you see, we have this with every subgroup normal in the next, okay? Because what have I done? No, well, okay, just a second. Well, okay, why not? Why not? I have mixed up things, but let me clarify. G is soluble. I only assume the yi to be normal in yi plus 1. Well, this is not a serious problem. Okay, let's fix this one. Here I use 3, but nothing prevents me here, since G over n is soluble, to take this yi normal. This is what I've done. Normal in G over n, okay? Is the second equivalent property. So this is a normal series, okay? With the quotient abelian. Because this is what I've done in the next slide, in the next page. I mean, it could have done just in one normal in the other. So, but what's important is that you have yi normal in yi plus 1 until you get to n, and then zi normal in zi plus 1. Actually, the zi are normal in the whole of G, but who cares, okay? What happens, I put together this series of n and this series of G over n, and this is, it's a mixture because it's partly a series and partly a normal series, but I mean, it's still a series, is a series for G with abelian quotients. A normal series, of course, is a series, so that's okay. Okay, and this actually makes simpler this part here. Okay, so if apart from the indecision here, but I'll fix this. I mean, I can choose any of the 3 equivalent conditions for G being soluble. For n, I have chosen this with every subgroup normal in the next, but for G over n, I can choose the other condition. And let me stress that the reason why I have chosen the series, non-normal series definition for n is because I'm not guaranteed that the xi are normal in the whole of G, because normality is not transitive. Whereas if I work on G over n, the third isomorphism theorem assures me that if the yi are normal here, then the zi are also normal here, okay? And that's all for today, thanks. And with next week, we start discussing representation theory of groups proper. Thank you for your attention.